Welcome in to another new AMP podcast. I'm your host, Ben Dubose, and I'm the news editor with the AMP publications team. In that capacity with the Association for Materials Protection and Performance, best known by the acronym of AMP for short, I create content for both Materials Performance Magazine, or MP, as well as for Coatings Pro Magazine. Today's episode is part of our MP interview series. For today's show, we're talking with Sean Clancy, Senior Director of Materials Science at HCO Incorporated. Founded in 2011, HCO emerged from a vision to make electronic products fully submersible. Soon, this vision expanded to a desire to revolutionize how and where markets, businesses, and consumers use electronic products with coatings that can sustain protection in the harshest environments. What started out as a small business in Salt Lake City, Utah, has now evolved into a global network of state-of-the-art coating facilities equipped with cutting-edge technology and a team of dedicated engineers. The group's headquarters are now in Raleigh, North Carolina, with a global presence worldwide, including China, Vietnam, and Mexico. HCO's journey has been marked by an unwavering dedication to exceeding the expectations of clients and pushing the limits of what is possible with protective coatings. So on today's sponsored podcast, we're going to be talking about why corrosion can be a major mode of failure within electronics for many types of manufacturers, even in some very high reliability markets such as aerospace and defense. But before we talk more specifics on those fronts, let's start with introductions. Sean, I mentioned earlier that you're the Senior Director of Materials Science at HCO. Can you tell us a bit more about that role and the types of projects that you take on?
Yes, thank you, Ben. I would say that I am involved in a variety of different aspects of the organization. So I help out with technical requests coming in from marketing and sales, as well as helping out in the development and measurement of coatings and coating processes, as well as helping out the production operations groups in terms of troubleshooting and or process optimization. So we do a variety of different coatings in our facilities. I would say that the bread and butter of our business is the Parylene type of conformal coatings, which are deposited under vacuum. So one of the great things about Parylene is that it coats everything within a coating chamber with a very uniform thickness, and it coats and it goes everywhere inside the coating chamber. One of the I'd say downsides of Parylene is that when it's coating, it goes everywhere. So even if you wanted to have it not go into connectors or different places, you have to plan for that ahead of time and mask off those areas. And you can use different types of glues or tapes or other types of mating connectors in order to help prevent the coating from getting in those zones.
Just to add some color to that, what are some examples of markets that you serve and who your typical clients are?
Historically, a lot of our business was in the consumer electronics market, which is was kind of unheard of for Parylenes because it's historically been a very high reliability market, like industrial devices, aerospace, defense, medical, space, and semiconductor. And while we did devote a lot of our business to consumer electronics, we've transitioned and broaden our portfolio into more of the industrial sector and more of the aerospace, defense, and semiconductor, as well as medical devices now.
What feedback do those users give you as far as what their unique needs are when it comes to materials protection? What are they seeking out? What are some of the unique challenges there?
I would say a lot of them have some very strict requirements in terms of the types of dielectric or electrical protection and chemical and moisture barriers that are required for their products. And depending on the application and or the types of products that need to be coated, might have very strict either coating thickness ranges or very, I would say, in one instance that was a recently published application with a group at NASA we had to deliver a very precise and coating thickness gradient across a sensor die over a very narrow area. And that was one of the more unusual and challenging instances we've had to overcome recently.
In terms of the science of all this, how does corrosion in electronics actually occur? What is the process like as far as just a general overview of what the threats are and how it ultimately plays out?
I would say a lot of the corrosion that you see in electronics are under what's called dendritic growth or electrochemical migration. And so for that to occur, you need three types of things. So you need ionic materials like salts. You need moisture, either bulk water or just a very fine amount. And you need an electrical bias. So salts and other types of residues, you can either clean off your product before coating, or you can block the introduction of those salts and ionic residues from getting to your electronics by coating it. In regards to moisture, again, you can either dry out your product before coating and keep it dry. And you can use coatings to block moisture from getting to your product. As for electrical bias, you can never turn your product on and you won't have it fail. But that's not likely to happen. So you kind of want to block the salts and moisture from getting to your product. And those are the big ones.
So we were talking offline before we started recording about the success or failure of coatings for these types of assets. And I know you've done a lot of root cause failure analysis over your career. And you were telling me that a couple of key variables are the state of cleanliness prior to coating and also the environments that the asset is subject to after being coated. Why are those such important variables? Can you elaborate a little bit about those two factors and the role they play and ultimately the success or failure of a project?
Sure. The state of cleanliness before coating can affect the reliability of the product in a number of ways. If you have a lot of oily or organic residues on your product, then you're going to have a hard time with any type of coating sticking well. And then if you don't have a coating sticking well, you are having the opportunity for, the unwanted things like moisture and other chemicals to more easily get to your electronics. If you have anorganic residues like salts, or a lot of the times it's flux residues, so solder flux residues. If you have those that are still ionic and active on your product and you coat over it, it's going to be a challenge. You may never have an issue, or you could have an issue depending on how long that product's expected to operate and how much moisture was in your product before you coated, and how much water can get to those areas where the ionic residues are underneath the coating. So ideally, and in a lot of instances, for very high reliability products, you clean with the appropriate cleaning chemical. It's either specialty detergents or saponifiers and the like that are well matched to the types of residues on your electronics assembly, and then rinsing it with good, clean, deionized water afterwards. And then you dry out the product, and then you can prepare it for coating. The thing is, cleaning well adds extra cost and time, which is, time is money, and all these extra processes is add up. So the electronics industry, at least a lot of types of markets that use electronics, have moved to what's called no clean processes, and it's usually specialty, less now specialty, variety of different solder fluxes, solder pastes, and the like that have materials that are not meant to be ionically active after it's gone through an adequate reflow soldering process. So it's heated well enough at the high enough and temperature and for long enough to fully have the flux do its thing and form good solder joints. And then it's meant to deactivate and encapsulate any types of residues that could be present. The thing is with these no clean soldering processes is that you want, or ideally, you want to show that there are no ionic active residues left on your product. A lot of people kind of skip that step of making sure that you don't have those no clean ionically active residues because they assume no clean means you don't have to clean. And that's not truly the case. So it's kind of a challenge in both. It takes a little bit more work to do it well. And it's also kind of like I would say, a technical marketing and education issue within the electronics industry.
And then in terms of the types of environments post-coating, what are the different risk factors there?
I would say some of the most challenging are in the aerospace industry, especially on airplanes where you have relatively normal or warm or generally normal temperatures when the planes are on the runway. But when they go at very high altitudes, the temperatures drop drastically. So if you have materials that can't withstand these wide temperature fluctuations and have good, well-matched coefficients of thermal expansion, then you can have either your coatings crack or lead to strong forces that can even break solder joints, or you can have, eventually it's a lot of the times, especially with parallenes, your solder joints are going to fail before the parallene does. So it really depends on what types of coatings you choose and what types of products you make and what kind of environments they are expected to operate in. Some other challenging environments are near the ocean, and there's very high amounts of salts and ocean spray, salt spray, and the like, and that's very challenging. Other environments include, I would say, any type of polluted air environments that could involve sulfurous gases, and those involve oil and gas industry, clay processing, paper mills, even onion and garlic processing facilities. So you have all kinds of electronics in all of those environments, and if they're not well protected, then the sulfur in the air will very quickly start reacting with the copper and other metals, especially silvers, on electronics, and just tear them apart.
You spoke a little bit earlier regarding the corrosion mechanisms. And so when we're talking about causes, I know there's some corrosive residues that can also occur during the actual manufacturing and handling processes for these pieces of equipment. What are the mechanisms there, and what are the risk factors in those phases?
I would say a lot of times it's, especially in the electronics industry, you have essentially acid etching baths that are used in the printed circuit board or printed board manufacturing steps. So you have to, put down a sheet of copper foil, laminate it between an epoxy prepreg resin. And then if you want to, make a trace path, you will have to mask off that copper with some tin, and then you put that exposed copper area in a bath of nitric acid, which you should then rinse off with good clean water afterwards. And then if your acid baths and etch baths aren't properly maintained or tracked, at least in the printed board manufacturing process, you could have some of these nitric acid residues left on your board, which could lead to corrosion and the like. For the components on circuit boards, you have different metal plating valves that are used for the metallizations of the terminals that you solder to. Those can involve various acids and other metal salts and the like. So if they are not adequately rinsed and during especially the final stages of the component manufacturing processes, then you have all those types of residues on your board. So you have component residues or potential component residues, you have potential printed board residues, and you also are then adding those to with solder flux, which is another type of potential residue. And then, you might have people handling them manually. So you have finger oils and finger salts and skin from your skin. And so it's amazing sometimes that electronics work at all.
Yeah, it sure is. We've talked a lot of this episode about the causes and the risk factors. In terms of the solutions, you outlined earlier the role of both coatings and cleaning processes, and specifically using them in tandem with one another, not shortcutting those processes. I know another potential solution that we've talked about offline are enclosures. How do those fit into these processes? What's the role of an enclosure? How can that potentially provide a solution for some of these issues?
Enclosures are kind of a double-edged sword in that you kind of have to think well ahead and make sure that they are well enough designed for the type of environment that you're expecting them to operate in. So if you have enclosures that are meant to be like IP68 or IP67 and the like, you're keeping out dust and water and everything. And, it sounds great, but if water gets into that enclosure somehow, then it's going to stay in there, and that might lead to a corrosive environment for the electronics inside. So depending on the application and industry, you might want to design your enclosures to have essentially vent holes or weep holes so that water, if it does get in, it'll drain out or it'll allow enough airflow to help it dry out. With that, though, you also have the opportunity for corrosive gases to enter and the like. So I kind of think of coatings and enclosures as kind of a belt and suspenders approach. It's not usually a great idea for especially high reliability applications to just depend on the enclosure to do everything you want in terms of protecting. It's better to have a backup with a good conformal coating on top of those circuit boards and circuit assemblies, so that if the enclosure fails in any way whatsoever, your product isn't going to go down.
In terms of the conformal coatings, which are obviously your wheelhouse at HCO, you guys are a relatively new company starting up in 2011. So you've been around for a little over a decade now, expanded a lot in that time frame. What are some of the types of technologies when it comes to your coating solutions that weren't around when you started? And along those same lines, where is the industry going in the next 5 to 10 years in terms of newer technologies and conformal coatings that might help with these types of issues?
I would say that there are materials now that are being at least used by us and by some other companies in developing more robust coating products in terms of hybrid coatings, like combining parallenes or plasma coatings with atomic layer deposition coatings, which have been historically used more in the semiconductor arena. There are a lot of environmental concerns for not just electronics and coatings, but for a variety of products, which has seen a lot of the coatings that have been used in the past couple decades starting to be phased out. So there's a lot of like PFAS, so polyfluoroalkyl substances and the like. So there's a lot of restrictions on those fluorochemicals, and so you want to have alternatives to those types of markets to meet those needs.
You mentioned earlier the importance of not cutting corners in the process when it comes to both using conformal coatings, but also doing the proper cleaning processes. What's the process like of convincing an asset owner, or an electronics asset owner, I should say, of the importance in investing properly? Because I'm sure you can save on the front end if you maybe don't do every step, but then the cost in the long run obviously can be much greater. How do you make the pitch when you're talking to clients or potential clients of why it's worth it to go the extra mile to protect these assets and to not skip steps in the process as they're doing so?
It's a lot of communication, a lot of negotiation, and it's just a lot of the markets and a lot of the customers that we've dealt with. They may still do a no clean manufacturing process, but they have it under a very tight process, very tight control. So yeah, it's not being cleaned, but it's not having any ionic residues present. So it's actually, they've done their job well in terms of implementing a good no clean process. And so in those instances, it's not, yes, they may not be cleaning, but they didn't skip the steps. It's more of they've done the due diligence in those manufacturing steps to prove that they didn't have to clean, which is good.
I asked you about the evolution of coating technologies over the next few years and where that may be going. Along the same lines, I wanted to ask you about an evolution in demand. Where do you see your markets going? Is there anything new coming in terms of the types of parts, the types of assets that they need protected? Is there anything that HCO is focused on in terms of, in market evolution that's likely to occur over the next decade as you prepare for whatever's next?
That's a good question.
I'm leaving it broad for a reason. Curious what generally you think there.
Yeah, I would say that there's a lot of growth in terms of, I would say, the Internet of Things and smart devices, not just for home use, but also in the industrial sector and in manufacturing, and then like Industry 4.0 and 5.0 and the like. So you have smart devices and smart manufacturing equipment talking to one another to help you maintain a high uptime in your manufacturing processes. So that requires, if you want to keep your manufacturing processes working well, and those manufacturing equipment, you want those pieces of equipment using very high reliability controllers and components that will be well protected in whatever environment they're operating in. I would say that a lot of various types of electronics have just always going to be miniaturized more and more. So you have more of an area to and more critical dimensions for coding. But I would say with that comes with challenges in terms of how close those connector areas and keep out zones are where you don't want coding, are how close those are to where you do want coding. And so if that involves, different masking technologies, that can be challenging sometimes, because ideally you want to have a decent amount of space, a couple. Sometimes it may be involved with a millimeter to 2 or even 3 millimeters would be nice to keep your coating and those components underneath the coating well protected and far enough away from the areas where you don't want coating.
Great insight there from Sean Clancy, Senior Director of Materials Science at HCO. Sean, before we wrap up the pod, for anyone listening that might want to get in touch with you or learn more about what you all offer at HCO, what's the best way for them to do that? I believe the website is hco.com. Anything else that you want to plug as far as potential sources of contact or resources where listeners can learn more?
I would say our website is our best means of contact. We have various contact forms there, as well as a good technical library of resources available. Our LinkedIn page for the company has a lot of good information as well.
Good idea. All right, with that, we will bring this sponsored episode to a close. Remember, HCO is a provider of conformal coating solutions for electronics and other products made for markets ranging from consumer electronics to medical devices, aerospace to semiconductors, and a lot more. If they can be of potential use to you or perhaps a resource that you would like to learn from, just visit their website at hco.com or the aforementioned LinkedIn page. All right, that will do it for today. On behalf of Sean Clancy, Senior Director of Materials Science at HCO, I'm Ben Dubose, News Editor with the AMP Publications team. And if you want more resources from us here at AMP or with Materials Performance Magazine, just visit our websites at amp.org, ampp.org, or materialsperformance.com. With that, we'll wrap it. As always, thanks to all of you for listening, and please come back soon for more episodes from the MP Interview Series.